Hello, everybody. Good evening if you're here in the time zone that I'm in, or good morning, or perhaps later than that if you're coming in from elsewhere. Welcome wherever you're coming from. As you're probably aware, there's a solar eclipse going on at the moment, seen mainly in the United States, and it's going to reach its peak in about 20 minutes time. So we shall work through that alignment, and how nice to be drawing lines and alignment at the time that Sun, Moon, and Earth are all in perfect alignment. Right, let's begin with some slides. I was reminded a few days ago by someone that I studied with at the Prince's School that the fourth anniversary of the death of our teacher, Professor Keith Critchlow, is today, April the 8th. And 4 years ago, when he died, it was a Paschal full moon. So the Paschal full moon is the full moon that happens during Holy Week. And of course, Keith, being Keith, he chose this rather amazing day to leave this world because, as well as being the Paschal full moon, it was also obviously Passover in the Jewish tradition, and also the full moon immediately prior to Ramadan back then in 2020, which is a very important full moon in the build-up to Ramadan. I think it's when the heavens open for the revelation for the Prophet Muhammad. So typically, Keith left on a very significant day. Now, here we are today, this time a new moon. And I'll explain a bit later on why solar eclipses can only happen at new moons, in the same way as how lunar eclipses can only happen at full moons. Now, it's a very simple thing when you sort of look at a diagram of it, but it's a rather beautiful symmetry that they have in that sense. And this is really very much the case with the symbolism of sun and moon. They are sort of, I suppose, opposites. They're oppositional lights, and you could say symbolically that the middle path that runs between them is really the middle path of ascent between heaven and earth. Perhaps more about that as we go along. Now, I'm sure that Keith would be very happy to be followed by this image here and this particular storyline. This is a character in Dante's Divine Comedy, Matilda in English form, or Matilda in Italian form. And she's a female character who is very important within Dante's transition into the Garden of Eden. She helps him transition into that state whereby he can fully enter the Garden of Eden. Now, when he first sees Matilda, when he gets to Eden, he associates her with Persephone, or Proserpina, as the name he uses. He associates her with Persephone in eternal spring. Now, the story of Persephone is that she's abducted from eternal spring, and the consequence of her abduction is that she has to spend some of the time below the earth in the darkness of the underworld and some of the time above the earth. And so she moves into this fluctuation between light and dark, but she comes from this eternal spring state. And Christians in the medieval world came to associate this ideal state, which is associated really with the Golden Age, according to Ovid. They came to associate it with the Garden of Eden because it's a very similar idea of an ideal state from which everything started, but from which everything, I suppose, fell to a certain sense. Now, I showed some images similar to this a couple of weeks ago, and we'll just look at them again, slightly different, because this idea of eternal spring is also associated with an eternal equinox, because of course the equinox is that midpoint between the two solstices, the light and the dark of the summer and winter solstices. So the equinox is this middle state of balance between light and dark. And John Milton, in his Paradise Lost, he actually associates the equinox with the pre-fallen state. So there's our polar axis. And here is what you could call the ecliptic. So this is, I suppose, the straight line that you can draw between planet Earth and the sun. From an earthbound perspective, it's really the course that the sun takes through the sky. Now, this is when you get to a solstice, where you have, it's actually the northern hemisphere winter solstice, because as you can see, the northern hemisphere is sort of facing away from the sun, whereas the southern hemisphere is facing more towards the sun. So that's the summer solstice in the southern hemisphere and winter solstice in the northern hemisphere. And this is when you have this extreme of its axis, 23.4 degrees, which I showed a couple of weeks ago, how that shows itself within the design of the nave in the cathedral in the city of Wells. So let's now go back to the equinox, and we'll go the other way this time. So this time, when you have the northern hemisphere facing towards the sun, then you have the summer solstice in the northern hemisphere and the winter solstice in the southern hemisphere. And again, you have that 23.4 degree angle. Now back to the equinox again, which is this middle place between those two extremities of the solstices. So as I said, eternal spring is associated really with Eden and with a perpetual equinox, because what John Milton says is that when the fall of humankind happens, that's when that 23.4 degree angle comes into play. But prior to that, there is this ideal perpendicular relationship of Earth's polar axis to the ecliptic. Now, I'll remind you how this shows itself in the design of the cathedral at Wells. Before I move on to show the eclipse angle or the inclination of the moon, which is in a different part of the cathedral. So here are the basic geometric coordinates, and it's that nave on the left there, you may remember from what I showed a couple of weeks ago. And the tropics of Cancer and Capricorn are essentially the north and the south wall of the building. And this is all knowledge that was known in the 12th century. It's not sort of odd to say that this would have been known about. So it was known about a long time before the 12th century as well. So there's every reason to put it into the design of a building. Now let's take a look at it again within the diagram of the whole cathedral, because of course the key point here is that the equator is the middle path of the cathedral, and that is the one that actually leads up to the Lady Chapel at the east end, which, as well as being based on the geometric shapes plotted out by the planet Venus, the morning star rising in the east, and so therefore being a place associated with the resurrection of Christ. But it's also an image of the Garden of Eden, which is on the far east of the world map, in a similar way to how it's at the far east of the cathedral building. So in short, you have these solstitial axes, which you could say are the side aisles, which lead up to chapels dedicated to solstitial saints. I won't say any more about that because I described that in the last session. And then the middle path between them, the equinoctial path, which you could say is the path of eternal spring, which leads back to Eden in the east, is that middle path. And it also passes through the choir, which, as I'll mention shortly, is associated with Jerusalem. Now, this layout of a building where you have Jerusalem, you could say, at the center or at the heart of the cathedral, Eden in the east, is something that you see on this image I've just put in on the bottom right-hand corner. It's the Hereford Mappamundi. Now, what you see with the Hereford Mappamundi is really a very similar idea of, I suppose, progress eastwards back towards Eden. So the Lady Chapel, which, as I say, is associated with Eden, perhaps I should just describe that a bit more. A Lady Chapel is dedicated to the Virgin Mary, and the Virgin Mary is known as the rose with no thorns. Now, there are thornless roses going all the way around the wall of the Lady Chapel in the cathedral at Wells. And this is to do with the idea that the rose, when it grew in Eden, it had no thorns. And it was through the fall of humankind that the thorns began to grow. And then those thorns are in turn associated with the crown of thorns that Christ wears during the crucifixion. So the thorns are the suffering of the earthly state, whereas the rose, I suppose you could say, is the true state of the soul. And so it's the Edenic soul. And in this sense, the Virgin Mary has that particular association. So her place at the east end of the cathedral is Eden. Now, Eden on the Hereford Mappamundi is that small circle there at the very top of the map, which is east. That's the way maps were made out in the medieval European world. Now, here we have Eden. Now, you might be able to see a little figure in the top left there. It's actually a sort of an upside down figure. I assume that must be Lucifer, the fallen angel. I mean, I have not heard anyone say that, but he's upside down and falling from heaven. So he must be Lucifer, the fallen angel, because his fall is often associated with the fall of Adam and Eve from Eden. So there he is depicted sort of next to Eden. Now, as I mentioned, Jerusalem is at the center. Now, the central perforation in the Hereford Mappa Mundi is right at the center of that circle there, which is Jerusalem. And if we look back at our image of the cathedral at Wells, the crossing, which is really the center of the cathedral, that is where the doorway is to the choir as you go in here. Now, the choir is the same shape and size in its ground plan as the Temple of Solomon. It has 6 bays, which each measure 10 cubits. And so you have this 60 cubit length of the temple. So you have Jerusalem at the center, and here's the image, a close-up of Jerusalem on the Hereford Mappa Mundi. Like I say, the central perforation with which the whole of that map is drawn is at the very center of Jerusalem. Now, from a medieval European perspective, you could say that the starting point, which is the nave, I suppose the earthly world from where the journey eastward begins, would equate with Europe on the map, because Europe is always depicted at the bottom left of what's known as a T&O map, whereas Africa is on the bottom right and Asia is at the top. So you have this progression eastwards, and the Crusaders did often talk about this idea of going eastwards towards Jerusalem. But of course, in the Far East is where the Garden of Eden is. Right, so let's start talking about this eclipse, which is happening at the moment, which we're nearly at the highest point of. Now, the solar eclipse is where you have Sun, Moon, and Earth in this particular order. At this point, when you have a new moon, that's where you have the moon in between the Earth and the Sun. And so the Sun is illuminating, you could say, this part of the moon. But of course, the part of the moon that we can see from Earth is invisible or is hidden. And so this is why you always are going to have a solar eclipse at a new moon, because of course the moon passes in between the Earth and the Sun. Now, if we look at a lunar eclipse, then they happen in this order. So Earth is at the center, and of course Earth is the one that is eclipsing the moon. And so you have a full moon because the sun is illuminating the side of the moon that Earth is also seeing. But when you have a perfect alignment between the three of them, then obviously there is a lunar eclipse. Now, this being the case, you would ask the question, why is there not a solar eclipse and a lunar eclipse every month? Because if they're in that alignment, then why is there not an eclipse each month? Now, the reason for this is because there's this angle associated with the moon, which is the inclination of the moon. And it actually creates, I suppose you could say, a not quite straight axis most of the time. But there are a few occasions when there is the possibility of this alignment between Sun, Moon, and Earth. And so that's what I'll describe with this diagram. So we've got Earth on the left, North and South poles, and the equator. So there's that 23.4 degree angle that I was just talking about earlier. Now, this horizontal line that's going through, this is the ecliptic. So that's that orbital plane that Earth goes around the Sun on. And what you have with this other line, which is going through the moon on the right there, is this slight difference of 5.15 degrees, which is the inclination of the moon as described in degrees. Now, what happens? The moon will go around Earth on this plane, which is slightly different to the plane of Earth around the sun. And so twice a month, it will cross over the ecliptic. And if that crossing that it does over the ecliptic happens at the right time, at the right point in the cycle, you end up having this perfect alignment between Sun, Moon, and Earth. So it doesn't happen all the time, but happens now and then, about every year and a half for a solar eclipse on average. Now, this angle of inclination is one that I've taken quite an interest in. It's definitely ancient knowledge. We know that it was discovered in at least, I think, 300 BC, but quite possibly before that as well. But it's written about around 300 BC by Hipparchus, the Greek astronomer. So it's ancient knowledge, not something that you need modern technology to be able to know about. So what we're going to look at is where this shows itself in three of the Gothic cathedrals that I've looked at, and they're all described in detail in my book, The Cosmos in Stone. So this is in chapter 9, as far as I remember. Now, this is the diagram, which, I mean, those of you who know about my work, you'll know I'm a very big advocate of this diagram. I think it's truly amazing. And the reason why I've become so interested in it is because it looks as if it was used in three of the Gothic cathedrals. And this is what I sort of write about quite a lot in my book. So let's take a look at how this works. Now, it's just the pyramid triangle there, you can see with the height of 7. And then the square, which gives the size of the moon, because what we have here, if this circle is the size of the Earth, this one is the size of the moon. So clearly we have an association of the moon with this octagonal building on the north side. It's known as a chapter house. Now there's various lunar, I suppose you could say numbers or qualities in the architecture around this area. So that sort of bolsters the idea that this diagram is consciously used by the designer within the design of this cathedral and a couple of others. Now let's take a look at another one, Southwell Minster. This is up in Sherwood Forest area, full of green men, especially in the chapter house. In fact, the octagonal chapter house is full of these rather amazing green men. Now, if we just take a look at the East End area, this is where the diagram works. Now, where the diagram begins is the beginning of the Gothic work, because this area here is older, it's Romanesque. But the Gothic work begins where the pyramid triangle starts here. And as you can see, the size of the moon square perfectly contains the octagonal chapter house. Now, let's look at the third one, because this is the one where it starts to get very interesting in relation to this angle of inclination that I was mentioning a little bit earlier. Now, York Minster, again, it has an octagonal chapter house on the north side of the building. But if you look closely at that chapter house, can you see how it's slightly skewed in its orientation? It's not in the same alignment as any of the rest of the cathedral. Even the passageway that leads to it is in line with the rest of the cathedral, but the octagonal chapter house isn't. Now, isn't that interesting? Considering it is a lunar space and it has a particular angle within it. Let's just take a closer look. So here is the diagram. Again, it works very well within York Minster, but we have this angular skew. Now, in short, it is the inclination of the moon. It's just over 5 degrees. And as I said, this is knowledge that goes back into the ancient world. So again, it's not a particularly odd idea to say that this would be used by medieval Christian artisans who are wanting to, I suppose, bring heaven down to earth by using cosmological aspects within their design. Now back to Wells. So now we're looking at a close-up of the chapter house at Wells. Now take a look at that small vestibule area that leads from the staircase into the chapter house. Again, it's a completely unnecessary skew in the architecture. And again, it's just over 5 degrees. Now, it's the doorway area where the skew happens at York Minster. So here, again, it's the door, which is that area that has the skew. Now, just very briefly, and there's a lot about this in the book, just to say briefly, there's also 29.5 steps in this staircase, which is the amount of days in the synodic lunar cycle. Now, there is that vault of that vestibule looking from down below. So you can see there is very clearly this skew in that area. Now, at Southwell Minster, there's a similar thing that happens, but again, it's slightly different in terms of how it's employed. There's no skew in the architecture as such, but the doorway that leads into this chapter house is off-center on its wall. Now here it is, here's the inside of that doorway. You can see how there's a seat on the right of the doorway, but there's nothing on the other side of the doorway because the doorway itself goes all the way up to where the following wall meets it. Now, in short, the pillar in the middle of this doorway, which divides those two slim doorways, is well, I'll say it's at the golden section of the wall, but it's actually a Fibonacci approximation of the golden section. It's 13/8. That's where that pillar is. And by being there, it picks up the lunar angle, because the lunar angle, I'll show you a closer diagram of it shortly, but the lunar angle ends up being about 1 inch off the center of that pillar. So that pillar picks up both the lunar angle and this particular golden ratio or golden section measure. So here it is. This is the line which goes along the east-west axis of the chapter house. And then here is a line that goes to the, well, just slightly off the center of that pillar. And you can work it out using mathematics. 5.15 degrees is there at that point, just slightly off center of the pillar. Now let's draw. What I want to do is actually get us to draw this diagram of Earth and Moon at those particular angles. So I shall get my camera ready. Right, perhaps I should say hello first as well. Hello, everybody. A different background today. I'm in a different place. I'm up in London, in my parents' house. So let's get started. Now we're going to draw on both sides of the paper, and we'll swap around from one side to the other. Now it's a relatively straightforward compasses geometry that we'll do, but then we'll do some slightly fiddly measurements on the ruler. So I'll perhaps repeat those measurements on more than one occasion as we go along, because there'll be slightly fiddly or precise measures that we're using from the ruler to get the angles in question. Now, I'll also possibly adjust the light as we go along, because obviously I'm in a different place where the light is slightly different to what I'm used to. Right, now let's begin by getting a point. It's going to be on the left side of the page. As you can see, I've got A3 paper in landscape orientation. And we want to come in 5 inches from the side of the page and 6 inches up from the bottom. So I'm going to come in 5 inches from the side and just sort of put my pencil roughly in place, and then go 6 inches up from the bottom of the page. Perhaps so I'll demonstrate that again. I went 5 inches in from here, 5 inches from that side, and 6 inches from down here. And so this gives me a point to work from as that dot. Right, now here is the first measure from the ruler. We want to have compasses at a radial measurement of 3 3/4 inches. So there you go. 1, 2, 3 3/4. Now, there is a reason for this, which I'll explain sort of as we go along. We're going to create the equator ecliptic angle. If you saw my session 2 weeks ago, I showed 2 different rational measures you can use to get that, and we drew the 7×3 rectangle. But we're going to do the 13×30 one, because that's more precise. That gives 23.4 degrees. So 3 3/4 degrees. Now, if you want to check just to make sure you got the right thing, if you were to check that in centimeters, it's roughly 9.5 centimeters. But do the inch measure. You can just sort of use centimeters to check. Because I've noticed when I teach with inches, sometimes people get halves and quarters and 3/4 mixed up. So 3 3/4 inches, and draw a circle from the point that you've put in the page. Now, perhaps we're presenting ourselves now with an image of what some people are actually seeing up in the sky. We're about 5 minutes past now, but there we have a circle of heavenly light in its or in an earthly form. Now I'm going to put the horizontal line through the circle, but I think I'm going to put it through the whole page. So if you want to be precise about it, I mean, you can do it by eye if you want, or if you want, because there's 6 inches between the center of the circle and the bottom of the page. If you want, you can measure 6 inches from the bottom corner of the page here up to here. And then you can do the same thing on this side of the paper. And you'll need to do one in the middle as well, though probably this dot should give us the middle one that we need. Yeah, that's fine. So I've put 6 inches up from here, 6 inches up from here. The center of the circle is 6 inches up. So I can use center of the circle with these points. And I'm going to go through this one as well. Now we're going to do that very beautiful and simple division of the circle, which is so very versatile. It gives you so many different divisions of the circle. In fact, I was in the church that I got married in this over the weekend, and there's a medieval consecration mark which has this geometry within it because it forms a cross. So as you can see, I'm doing these two crescent moons, you could say, over the circle from the eastern and western points, or eastern and western points of the circle. Now, usually at this point, I would suggest to do this, but obviously we'll go off the page if we don't reduce the compasses. So I'm going to reduce the compasses. It's not really a particular reduction you need to make. You just need to make sure that the marks that you're about to make from here and from here will fit around this area here. So reduce the radial measurement on your compasses so that you can do that. So as you can see, I've reduced them, and there's no particular reduction other than just so that it will fit somewhere above the circle. Now I'm going to do the same thing as above, so below, you could say. And this, as you're quite possibly aware, if you do geometry regularly, this is how we get the bisector. Bisect means, of course, to cut in two. And this, you could say, is the middle path between east and west, if you want to look at it in that symbolic way. And this line that you can now draw should hopefully go through the middle of the circle and give us north and south. Right, now importantly, the next thing that we need to do is to put the radial measurement of our compasses back to what we started with. So don't use your ruler, use the circle as you have it on the page, and go back to the original radial measurement. Now, when I do this, I always check sort of on both sides just to make sure I am in the center. Top and bottom as well, you might as well. Now, once you've re-established that radial measurement, we're going to do 2 more semicircles from those 2 new points that we've established at the top and the bottom of the circle. And once you've got, now make sure that you do actually have the tips of these petals. So you may find that you need to make your semicircles very slightly bigger so that you actually have the tips. Because what I'm now going to do is join those 4 tips up. And create a square. And this square, of course, has the same, well, its edge length is the same as the diameter of the circle. Right, so as you can see, we're doing a mix of compasses geometry, but we're also using units because that's what we need to do to get these angles that we're using, these cosmological angles. Now, you should hopefully find that the edge of your square is 7.5 inches, which is, of course, double the 3 3/4 inches that we used for the radius. Now, the reason why we've got 7.5 inches is because in terms of units, I'm using 1/4 of an inch. So 1, 2, 3, 4 units in each inch. So 4, 8, 12, 16, 20, 24, 28, and 29, 30. So we've got 30 half or quarter inches. So that gives us that measurement of 30. Now, what we're going to do is now get a measurement of 13 going this way. And this is where we need to be, it's a little slightly more obscure, the measure that we're going to use. So I'll give a bit of time for people to get it. Now, I'm going to turn my paper around this way just because it makes life a bit easier. Right, now here is the slightly obscure measure we're going to use. If you go to 1.5 on your inch ruler, 1.5 inches, but then go 2/16 beyond that. So it's actually in all, if you've got your inch divided up into 16, it's 10/16. So like I say, go to the halfway point and then go 2 more little increments to the right. Now, once you've got that measure on your ruler, put that measure here at the midpoint of that edge of the square. So place that there, and then where you have the beginning point of your ruler here, make a mark. Now, so there's my mark that I've made. Now, like I say, it's 1.5 plus 2 more 16ths. It's 1 inch and 10/16 of an inch, if you want to be really precise about it, or 5/8 of an inch. And here's my mark, which is that distance from this point here. Now we're going to do a similar thing up at here, we're going to use the same measurement. This time I'm going to put the 0 point of my ruler onto there, and then I'm going to make a mark, again, using that same measure, like so. So again, 1 inch, ½ inch, and then 2 little 16ths. Now, what we've actually got here is, if this is 30 units going in this direction, this is half of 13 units. So this is why it's a bit of an obscure measure, because if we go a similar amount in this direction, which we don't actually need to, but that would then give us 13 quarter inches, 1, 2, 3, 4, 5, 6, 7, and so on. So all we need is this, and I'm going to draw a line. This is that line that runs at 23.4 degrees. This is the axial tilt of Earth. We don't really need to draw this, but it just gives a bit more of an idea of what it is that we're doing. We're actually going to just use these 2 points here and prick holes through to the other side. Now, once you've got that, we can put our paper back around like so. Right, now here's another obscure measure. If I'm going to turn my paper back like this again, and I'm going to, now I just, what we did where we did 1 inch plus 10/16 of an inch. I'm just going to take 10/16 of an inch this time. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm putting that 10th little mark like so, and then doing a mark like this. So again, that's 10/16 of an inch from here. Now I'll describe what we're doing shortly. I'll just get us to draw it first. Right, what I'm now going to do, I'm putting my ruler this way round because my inch markings turn into decimal divisions after a while. So I'm going to stay with my 16ths of an inch, which are at this end of the ruler. So I'm putting 7 inches onto the midpoint of my diagram so that my ruler runs down the line here. If you've got 16ths going all the way up your ruler, you won't need to do this, but I just need to do this because I've got, like I say, they become decimal once you get to 6. Now, what I'm going to do with 7 inches on that point in the middle, I'm going to go right up to the beginning of my ruler, but come in 1/16, 1 increment. Now, what we're going to do now, I'm happy for us to just use your eye to do this. If you want to be really precise, you can use your compasses, but I'm going to get us to just judge with our eye a small distance that's perpendicular to this line. I'm going to take that 10/16 again from that point that we just made and do a little point like so. So I've got my dot I've just made here. I'll make that a bit stronger. Now, basically what we've done is we've got this very slim rectangle, which is basically 10 by 111 units. So that's the reason for the obscure measure, but go with me on it because that's what gives the inclination angle. It gives roughly 5.15 degrees. And so once we have that mark there, then we can put in another angle. Now I might as well put this, I'm going to put this all the way through the page, in fact, because it will be useful for us shortly. So as you can see, I've gone from the center here through that point that we made, and I've gone right to the end of the page. So let's look at what we've got now. So just to recap, that is 1 10/16 of an inch, as is that. This is just 10/16 of an inch, and that is, well, 1/16 of an inch less than 7. Okay, let's just begin by putting pinprick holes through that point there and this point up here so that we can see them from the other side. Right, so I'm going to turn the paper like this. So I'm going to take the top of the paper and bring it forward like that. And this is the way that we'll work with it from here. Now, hopefully you can see the center of the whole diagram. So this point here, as well as these 2 points here, which will of course have taken on a different orientation. There's one up there and one down here. Now let's get another measure on the ruler. This is going to be the measure of the Earth because we're going to do the Earth in relation to the Moon. Now this one, again, it's another odd measure. If you go, first of all, you can go to 1.5 and then come back 2 increments. So it's 1 inch and 6/16 of an inch. So rather than going ahead of that halfway point, we're coming back 1 6/16. And here we have our planet Earth. And you should hopefully find that the diameter of it is 2 3/4 inches, which is basically 1/4 of 11. That's why we're doing this, so that we can sort of have something, because the diameter of Earth, if it's 11, the diameter of the Moon is 3. Now I'm going to go to these 2 pinprick holes here, and I'm not going to draw the whole of that line in. I'm just going to draw the line. So I'm lining up those 2 pinprick holes, but I'm only going to draw where we have that. Now, the next thing that we need to do is go back to the other side. And now we're going to bring the ecliptic line into our view. So I'm going to just make a little pinprick hole, one on this side at the beginning of the line there, and one on this side. And I can, again, use that central point to get the whole of the line running through. Right, I'm going to get North and South Pole just by doing a simple bisector. So I'll probably rub these bisector crosses out eventually as well. So you can take, I mean, you can take any measure you want really, as long as you use the same one from the 2 points. A bit further up. Like I say, I'm probably going to rub these out shortly once I've used them. Now, I'm not even going to put the polar axis in. I think I'm just going to mark north and south. So I don't want to put too much into the diagram. So I'm just going to do a little mark here and a little mark here. So from where those crosses uh, meet, and then I can just put a little dot here for the North Pole and one here for the South Pole. And once you've done that, you can rub them out, or you don't have to. Just so extra. Right, so now I'm going to put an N here for North Pole and an S here for South Pole. And here I'll put equator. And 23.4 degrees, which is what you get if you have a 13 by 30 rectangle, which that is essentially the diagonal of. Now, while we're about it, let's also write ecliptic, which I'll write over here. Now, the final thing to bring in is, of course, the inclination angle itself. So um, let's see, I'm going to get a particular measure for us to use. And I've never think right, let's get the measure onto the compasses. Quite a small measure on the compasses. The radial measurement is 1, 2, 3, 4, 5, again, 6/16. So a very small measure for the moon. This makes it so that the moon is um, the correct size. Now, I just realised I can't quite remember how I got this measure. It is a correct measure, because my ruler annoyingly goes into decimalized inches. I'm going to have to just give you a slightly, let's see, actually, I'm going to do something to remedy that. Just bear with me for a second. Right, let's do this in two. So I don't know if you have a ruler similar to mine where it goes in 16ths of an inch up to here, and then it goes into decimal divisions, which isn't useful for what I want. Right, so what I'm going to do first is just measure 5 inches along this line like so. Make a little mark, because obviously this is our construction layer. And then I'm going to go a little bit further up the line. So I'm going to go to where my 5-inch measure is made, like so. And then I'm going to do, now this one, let's see, this is a, I think it's another 3¼ inches. So 5 inches, 3¼ inches. And that's where I'm going to make the final pinprick hole. So you should find you have a pinprick hole around about here. And then, as I mentioned before, the radial measurement that you're going to need for the moon is 6/16 of an inch. That's the radial measure, and then this one goes in like so. Now, the reason why I wanted to put the moon in a very particular place, because obviously the moon is much, much further away from Earth than this diagram suggests, but it is a fractional unit of distance away. It's actually 1/10 of the mean distance of Moon from Earth. So now we've got that, I'm going to put the final line in, which is our inclination line. And that gives us the 5.15 degree inclination angle. Now, basically, this fractional unit that we've used of distance is, well, if you take planet Earth, and then if you go like this, 1, 2, 3, so it's 3 diameters of Earth, because also I show in my book here, this is from page 125 of my book, because of this 11:3 relationship of Earth to Moon, 3 Earths put together is the same as 11 moons put together. Now, if you multiply this distance by 10, you get the mean distance between Earth and Moon. So it's just another way that 11 and 3 show themselves with the relationship of Earth to Moon. So we've basically got 1/10 of the distance here with the scale diagram. Right, everyone, that's a very particular type of geometry that we've done there. Probably about the most units orientated geometry that I think I've ever taught anywhere, in fact. It's very fiddly. Because this is a recording, obviously it will be online. And so if you've missed any of those measures, you can watch the film and press pause as many times as you want. So take a look. I'll put it on, I know, tonight or tomorrow. Now I'll just put a few more, show a few slides again before I finish. Now, I want to remind you about this set of 8 courses I'm going to be running from Michaelmas time, from September of this year through till August of the following year. One course on each of the 8 points of the year. Now, you can come to all of them or you can come to just some of them. So be in touch if you are interested in doing any of them, and I can give you more details. Now, another thing that we're going to be running, this is a course run by Kairos in Wales. Kairos was Keith Critchlow's educational charity. It's still going, even though Keith is no longer with us. It's run by his daughter, Amanda Critchlow. And we're going to do a course in Wales. It's going to be myself, Daniel Doherty, and Adam Tetlow. We all studied together at the Prince's School. And we're going to do a course about the sacred tetractes. Now, the tetractes, this is something that Keith talked about a lot in his work. It's a form that the Pythagoreans would swear an oath over. And as you can see, it's a triangle of 10 dots, 1, then 2, then 3, and then 4. So hence tetra, because of 4 levels. Now, one of the reasons why we're doing it in Wales is because there are 5 of these tetractes shaped windows up at the east end of the cathedral in the Lady Chapel, that place that I'm saying is Eden and the Resurrection. So that's why we're basing the course there. So have a look at those details there and feel free to come along to that one. That is going to be in, of course, early June, 7th to the 9th of June. So do come along to that if you're free and interested in that particular subject. Now, the next session is going to be at midnight. If you're feeling like some nighttime geometry, do come along. It will be Monday, April the 24th at the full moon. So that's all for today. And thank you for coming along. I'll say a goodbye.
Thanks, Tom.
Okay. Thanks for everyone for coming. It's
Thanks, Tom.
really enjoy doing these, and it's really great to have all of you join me.
Thank you so much, Tom. It's great. I mean, just wonderful meditation.
Thank you very much, Tom. Very good.
Come again.
Thank you, Tom.
In a couple of weeks' time. Okay. Thanks.
Lovely sharing it. Lovely sharing it with everyone too.
Oh, it's my pleasure, definitely.
Thank you. Thank you. So the world. I'm very envious of those in America that have seen it in North America.
Yeah, same here. Well, I saw someone on the chat saying that he was in the right place, but he didn't have the right weather, which I'm sorry to hear that. But I hope that this has been a good second best thing, hopefully.
Absolutely. Thank
Okay.
you.
Thank you, Tom.
Okay, bye. See you again. Thanks for coming. Bye.